right, it's time to get started. Here comes the live stream link for the chat. Hold on one second, I'm checking in on a direct message. Okay, super duper. Let's get going. What do we got on deck for today? We're talking about linear systems of ordinary differential equations. We got WebAssembly number 12 coming in today at 11:49 or 59 p.m. And then an announcement will be made probably after class today. It's been all drafted up, but we're doing the last checks on it. And it's just another announcement. So on the 7th, we announced the projects. On the 19th, we supplied the rubric to the projects. And now what we're doing is we're giving a little insight into the format that we'd like to see in terms of just layout and expectations there. And then I think the only other note is that there's one quiz, 2 web-assigns, 1 worksheet left. Yeah, I think I've got the YouTube link. I'm sending it back in. Here we go. Boom. All right. There's the YouTube link. And then, let's see, something just disconnected from my computer that allows me to very easily change these graphics here. So just a second. All right, and then what do we got on deck for today? We got to look at complex and repeated roots and just look at the way we're going to treat those with linear systems. So that's what's going on. We'll do a little bit of review and then hit hard these cases. We've started a bit on complex, but let's just practice. And so let's see. Here is the set of notes for today. Starting in here. I will bring myself back. Okay. So, step 1, you got 2 differential equations. They're linear in the xy variables. They got constant coefficients. You can rewrite this linear system as a matrix equation x prime, where the vector x holds both the little x and the little y data, and then matrix A times vector x, where matrix A holds the coefficients a, b, c, and d. We're going to search for solutions that are of the form x of t, y of t. First component is a function of time. Second component is a function of time. And it is a vector times one exponential that's shared between the 2 components. And that exponential has a rate constant in it of lambda. And then if you make this assumption where this vector right here is v, what you're going to find is from this differential equation, what you get is that it results in an eigenvalue eigenvector problem next. Okay. And then if lambda 1 is different than lambda 2, your Wronskian will be non-zero. The Wronskian is made by taking this whole column of data. Remember, the exponential can be multiplied into the vector. Taking that whole column, treating it as the first column of the 2 by 2 matrix, and then the second function that you get, because lambda 1 is different than lambda 2, you treat that as the second column of the matrix. You take its determinant, a la second order stuff style, figure out that it's non-zero, and those are linearly independent solutions. And so then the solution to the original matrix differential equation is going to be the linear combination of the 2 eigensolutions, you could call them, and that is also called the fundamental solution set. Okay. I was just checking in on chat. The trick is that this face has no actual emotion. Like if we were to peel back the layers, we would just find metallic parts and wires. Okay, so it could be the case that the eigenfunctions, right, these functions right here, which are the solutions to the differential equations, right, could be complex valued. In this case, it can be shown that the real and imaginary parts of just one of the 2 solutions are linearly independent solutions to the same ODE. That's part of the theory. We don't have to verify that every time. We just know that it's out there. So what I want to do is I want to put the 2-minute timer up, and I want us to take a try at decomposing this eigenfunction. But before we do that, I remembered that what I wanted to say is before we start up, what we want to do is we want to recognize that this e to the complex eigenvalue t by exponential rules is e to the negative t times e to the square root of 11 times I times t. So the first thing you're going to want to do is apply exponential rules to split out that real exponential. And now in the next 2 minutes, what I want us to try to do is just practice decomposing this. The more practice we do at this, the better we will be. All right, there goes the 2-minute timer. I've got my stuff set up to be a spot where we can just dive right in. So, in general, what's the worst you might fare for these complex roots? Well, you're going to get some complex eigenvector, right? And then you're going to have this e to the negative 1 plus square root 11 it. So the exponent in this exponential function could go complex, but you'll just multiply this t through, and then e to the negative t, which is e to the negative 1 times t, will just hang out front, and then the rest will be an e to the imaginary number where you just decompose that into sines and cosines, right? So forget about this e to the negative t for a little bit out front. It's not that big a deal. The game is played by taking these cosines and sines and multiplying them into the vector, right? Because then when I multiply them into the vector, as I've done with the first row, what I want to do is I want to keep an eye out for this purple term versus this green term. The green term is different than the purple term because the green term has an imaginary number I on it, right? And at the end of the day, what do I want to do? I want to sort this vector into two components, one that has imaginary numbers and one that does not, okay? So one of the two components in your vectors will just be like some real scalar. It won't be a big deal. The worst thing that can happen to you here, other than these square roots of 11, which are not the greatest thing to have to write, but they're okay. They're just a number. The worst thing that can happen is that you have a complex number in one of the components of the vector, and then you have a complex number sitting outside of it, right? Real number, imaginary number added together, that makes complex. And so you got to bring all this into the second row and do a bunch of foiling. You might have done that foiling. You might be finishing up with that foiling. Let's do the foiling now together, and we'll do it with one step. And what I want to do is I want to write my purple terms first and my green terms second. And what I mean by that is I want to just grab the real parts, write those down first, and then grab the imaginary parts and write them down next. So this is ready to be broken up. Okay? So when I do the foiling, right, I'm going to have this cosine function come in and hit this negative 2. So these two functions will get multiplied. I recognize that when these two functions get multiplied, I do not get an I, so I get a negative 2 cosine square root 11t, and that term is real. Okay. Now, when I take this cosine square root 11t and multiply it right here, when I do this multiplication, right, I'm going to pick up an I on that cosine, and that is going to turn that term into an imaginary term. So I'm going to pause on that, right? Now I take this I sine right here, I FOIL. The first place this I sine is going to hit is this -2, and when it hits this -2, I have an I on it from the I sine term, so it's going to be an imaginary term. And then the last term that I'm going to hit here is I times that negative square root 11 times sine. When those I multiply and I get an I times I, that will give me a -1 times the already existing negative out in front of the square root, so I will get positive square root of 11 times the sine of the square root of 11t. And that term is also real. Okay. Now, what I'll do is, in the foiling process, we did notice some imaginary terms come out, and so let's gather those up as well. I have this cosine term, and it's going to be hitting this negative square root of 11 times I. These two will hit one another in multiplication, and so I will get the square root of 11 times I times the cosine of the square root of 11t. And then I will get an I sine times a -2, and that will pick up an I, and so I will get a -2i times the sine of square root 11t. Okay. Kind of snuck off the page a little bit in terms of the resolution, so I'll zoom out a tad. And now, what does that mean for me? That means that my solution to whatever differential equation that this came from is equal to, okay, I just grab all the purple terms, make that into a vector solution. I grab all the green terms, that too is a vector solution, so I will get C1 e to the -t times, and then I'm running out of horizontal space. So instead of writing cosines as COS, I'm just going to write a C. So I'm going to get 5 cosine square root of 11t. And then in the second component, I'm going to get -2 cosine square root of 11t plus the square root of 11 sine square root of 11t. Add that to C2 e to the -t. And then I'm going to get 5, and then I have a sine function, so I'm going to write s times the square root of 11t. And then I'm going to get a negative square root of 11 sine, or cosine, square root of 11t, and then I'm going to have to sneak this down here. -2 sine square root of 11t. Okay. And then, just since things got crammed, let me highlight where these terms came from. All right. Cool. So that is the strategy. Once you get your complex root, then you will find a complex eigenvector, and then between the eigenvector and the exponential, you have one solution. You could find the other solution. They're just complex conjugates, but you don't need to. You take your first eigenfunction, you break it down into its sinusoids, you multiply everything together, you gather up terms based on whether or not they have i's or not, and then you use the purple terms as one solution, the sinusoid-based solution, and then you use the greens for the second linearly independent solution. And then the question that will come up here typically is, yo, all these terms had i's on them. Where'd those i's go? Well, remember, any multiple of a solution is a solution, and so I'll just write down the general multiple C2 of the functional pieces of that solution. All right, good time for questions. Are there questions about any of the moves, any of the symbolics, any of the ideas? Sean is asking in chat, so C2 eats up the imaginary number I. That's one way to think about it. It's not entirely precise. If you go into like the full bore of symbols, you see that that's not quite what happens, but as a rule of thumb, that won't fail you. That is totally fine. And so, yeah, if you in the future want to say eats it up, then that'll kind of also trigger that it's a little informal, but it works and it has the same effect. So we never really have to put imaginary numbers in the solutions. Yep, that is absolutely true. How can we use this in the real world? Well, what we are looking at in a mathematical form is an underdamped mass spring system. So there will be oscillations with amplitude decay. And why would we be tracking two things at the same time? In a mechanics problem, there are two things that you typically want to know: displacement and velocity. What we're doing right now is we're tracking both displacement and velocity of some sort of mass spring system, which I haven't told you about, right, at the same time. And then what would we see? We would see that those things oscillate. So what this function here does is it forms a spiral that goes into the origin, kind of like water going out the hole at the bottom of a bucket. Cool. So what I'm going to do now is I'm going to move us over to another problem, and I'm going to give us a minute to start this up. Find the eigenvalues of this ordinary or system of ordinary differential equations. All right, timer's done. I'm going to get back with it. I wanted you to try that for a minute because I'm hoping that you didn't. Actually, I don't really care. If you did do the following, then it's a great lesson of something to be aware of. If you didn't do the following, then that's fine too. But you should also be aware of the error. So would somebody just tell me in order from upper left to lower right? So going one, number, upper left, upper right, lower right. What are the entries in this matrix A?
-3.
Yep, so we start off with a -3, and then we get a -5, and then we get a 3, and then a 1. Okay, so what I'm going to do is I'm going to highlight this -3, because this -3 comes from right here, right, because it's the term on the x. I want to think that the first column of this A matrix contains the x's and the second column contains the y's. So a common mistake that could happen right here is that the -3 and the -5 get flipped because we aren't paying enough attention to the letters, the variables that these coefficients hit. Okay, so if you made that mistake, that's fine. That's totally a common error, but you'll get a different matrix, and that matrix will have different eigenvalues as a result. Oh, I have a typo or something like that. That got erased. Yeah, that should be a Y. Yeah, good call. Good call. Boo, bummer for me. Bummer for me. Yeah, I think a Y was there and it got erased. And then I was so focused on this -3 game, right, that I didn't notice that. So keep an eye out for this 1 being associated with really that Y. Good questions in chat. It makes me happy. People are here and they're paying attention. So that's good. How could I? I'm sorry, Nate. All right. So step 1, I'm going to find the determinant of A minus lambda times I. That's going to be lambda squared minus the trace of lambda plus the determinant. And that's going to be lambda squared How do I find the trace? The trace is found by adding the components from the upper left to the lower right. So I get a -2 plus a 1, which is a negative, or yeah, a -2. And then I have another negative on there, so I get -2 times lambda plus the determinant. The determinant's going to be -3 times 1, so that's -3, and then minus a 3 times -5, so then that means, what, plus 15. I get -3 plus 15, and so what should I get from that? 12? And so I get lambda squared plus lambda plus 12. Is that right? Let me know if that's not right. I set that equal to 0. So now I get lambda is equal to -1 plus or minus the square root of 1 squared minus 4 times 1 times 12 all over 2 times 1. So I get -1 plus or minus the square root of 1 minus 4 times 12. The b value should be 2. Oh, yeah. Good. Thanks. I got so caught up in whether or not I calculated that determinant right that I just dropped a 2 right here. Okay. And so let me rework this quadratic. Thank you very much. So I get -2 plus or minus the square root of 2 squared, but that's 4 minus 4 times, this feels much better. Okay, times 12 all over 2 times 1. And so I get -2 plus or minus. And then check this out. In this square root, both terms share a 4, so I can just factor that 4 right out. And so I'll have the square root of 4 times the square root of 1 minus 12 all over 2. So I get -2 plus or minus the square root of 4 is 2. And then I have 1 minus 12, so that's the square root of -11 all over 2. And so that gives me -1 plus or minus the square root of 11 times I. Okay, there we go. So I guess I phrased the question, suppose we were told this, right? But I've just calculated that so that we see a nice, gross quadratic equation. And so now, part 2 is I got to find my eigenvectors. And so I'm going to look at case lambda 1 is equal to -1 plus the square root of 11 times I. And so I'm going to get A minus lambda 1 times the identity matrix times the V vector is going to be equal to, okay, I take my A matrix and off of its upper left to lower right main diagonal, I subtract my lambda. So I have a -3 minus parenthesis. Put a parenthesis right here. Please, 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 because what is being subtracted from the -3 is -1 plus the square root of 11 times I. And then I have a -5 in that second position in the first row, times v1, v2 is equal to the 0 vector. And that's what I've got. Okay? We need to make sure to put the parentheses right here, because if we do not, then this negative will only affect the real component of our complex root, and then we'll be off on the imaginary term by a sign. So please keep track of that. Next, notice I'm getting cavalier about this. I'm not even going to write the second row. The second row will tell me about the same eigenvector if I've done part 1 right and calculated my eigenvalues correctly. So I'm not even going to worry about doing the computations on that second row because I wasn't even going to use it. And so now I'll just use my first row, and I will get -3 minus a -1, so that's going to be a -2 minus the square root of 11 times I. All of this is times v1. I'm looking at the chat question, and Henry, I'm not quite following it. And then minus 5v2 is equal to 0. So my equation is actually 5v2 is equal to negative 2 minus the square root of 11 times I times v1. And so now right here, I would choose v1, and then that would uniquely determine v2 because I only have two components here in my eigenvector. It's a 2 vector. And so normally I would choose v1 to be equal to 1. That's just my standard go-to. But if I solve for v2, then I'll divide both equations by 5, and I'm going to get all these 1/5 lying around. And I don't really want that. And so what I'm going to do is I'm going to say let v1 be equal to 5. And if v1 is equal to 5, then that means that v2 is equal to, v2 is not a vector, eraser, come back here, okay. v2 would then be equal to negative 2 minus the square root of 11i. Okay, so then up above here, all right, that means my eigenvector v1 is equal to 5 in the first component, negative 2 minus the square root of 11i in the second component.
So I got a quick question for you.
Sure.
So does that mean that for notation wise that we don't need that vector hat on that V until we turn it into a matrix?
Yeah, that's a kind of a sore spot with linear algebra because in textbooks what you would also find is that the vectors would be typeset in bold and that the scalar components wouldn't have that bold typeset. So the best we can do with our handwriting is that we will only put the arrow on when we've collected the 2 bits of data and put it in a matrix form, as you said. So this v1 here could be a little bit ambiguous, but if it's got a vector notation on the top, it means it's the collection of the 2 scalars. They themselves have indexing as well. All right. So then for step 3, we want to form the general solution by, well, what are we going to do here? We're going to find the real and imaginary parts of v1 e to the negative 1 plus the square root of 11i t. But what do you know? In the example that we just did above, we found the real and imaginary components of exactly this vector. Here, I'll zoom out a little bit. We had the vector 5 in the first component, negative 2, negative square root of 11i in the second, and then e to the negative 1 plus the square root of 11i t. So this vector right here, which we have just found, what would we need to do next? We need to perform the decomposition operation to get the general solution, and that's what we just did up here. Cool. So I'm just going to write a little note down here, see above. Okay. Other questions? So when you get complex roots, proceed as usual to find the eigenvectors, right? You're still going to play the game of letting one of the 2 components, v1, v2, to be equal to some number to fish out the second. One of them will be complex or at least have imaginary numbers. Don't forget to use your parentheses when you're setting up the A minus lambda I matrix so that that negative gets distributed properly over your complex eigenvalue. And then at the very end, what do we have to do? We have to write down eigenvector e to the eigenvalue and split it out into its sinusoid forms defined by real and imaginary parts. Okay, so I'm going to fade. I'll freeze. And then I will come back in 3, 2, 1. All right. Last of the cases, the repeated root case. Okay. So let's just work this problem. Suppose that the A matrix is 0, 1, -4, -4. Let's put a minute on the timer. I'm going to move my floating head down to the lower left. And I too, at the same time, will find the eigenvalues of this matrix. All right, minute timer's done. For those that were working the problem, you set up the determinant of A minus lambda I. That will be lambda squared minus the trace of the matrix. So the matrix trace is given by adding the main diagonal components. So 0 plus -4 means that I have lambda squared minus -4 times lambda plus the determinant, which is upper left, 0 times lower right. That gets me a big goose egg of 0. Minus lower left, which is -4 times upper right. So I have a negative times a negative, and I get a positive 4. That means my quadratic equation is lambda squared plus 4 lambda plus 4. So what is the eigenvalue? It's a repeated eigenvalue, but what is it for this matrix? -2s are coming in. Wanted to make sure that that was out there, right? It is -2, not +2 if you happen to have gotten that. So now I'm going to work A minus lambda I. I'm going to subtract that -2 off the main diagonal here. So I'm going to get -2, 1, -4, -4 minus -2, multiplied by V1, V2. And then set all that equal to the 0 vector. Okay. So what's my equation? My equation is 2v1 plus v2 is equal to 0. So I get 2 times a v1, that's this term, plus a 1 times a v2, that's this term. I set that equal to 0. And then if I let v1 equal 1, then that would imply that v2 is equal to -2. So my eigenvector in this case is 1 in the first component, -2 in the second. Okay. So there we go. We've got a repeated root. It has only spawned one eigenvector for us. Now let's take a look at the game. I've written this down. I'll say it. It's nothing you need to write down, but this is definitely the motivation and thought process. With only one eigenfunction, we do not have enough linearly independent vectors to write down the linear combination of 2, or what I will say is span the two-dimensional space. That's foreshadowing. We don't know why we're talking about a two-dimensional space right now, but know that what we really need are 2 linearly independent vectors, because secretly this solution lives in a two-dimensional plane, and I need to be able to communicate with that plane, so I need 2 linearly independent directions. Okay? Key issue number 2. This system is equivalent to the ODE, and we haven't talked about why it's equivalent yet, but know that it is to y double prime plus 4y prime plus 4y is equal to 0. Okay? with my vector being the y function and the y prime function, first row, second row. This idea that I'm tracking displacements and velocities. So here's the issue. If I wrote down my solution to this problem, I would have written C1 e to the negative 2t, but then C2 times t times e to the negative 2t. So it turns out that I get this t multiplication. That's nothing crazy. We've seen that before. And so if I am, in fact, on some meta level that we will get into, tracking y and y prime, two functions at the same time, my y prime would be, all right, let's just do it. Take the derivative. C1 doesn't care about that derivative, so I get negative 2 C1 e to the negative 2t plus, what am I going to have to do right here? Because of the t multiplier, because of the repeated root, I picked up an extra t multiplier and I have to use the product rule. So what I'm going to do is I'm going to take the derivative of the exponential to get negative 2c2 t e to the negative 2t and leave the t alone. But now I'll take the derivative of the t and leave the e alone. And so I'll get c2 e to the negative 2t. Okay. What I need for you to do now is to check out the following. Look at this term right here that I'm highlighting in yellow, the first term of each of the two equations. Forget about the C1 and the e to the negative 2t. Say I wanted to write this as y and y prime. I'm tracking two things, so I might as well write it as a vector. I could have a C1 and then an e to the negative 2t hanging out. Tell me what goes in this two-component vector. First row, then second row. A 1 and a negative 2. Hey, I've seen that 1 and negative 2 before. Isn't it the eigenvector of the matrix? So what are these eigenvectors we're finding? If the problem came from like a mass spring problem, then the eigenvectors that you're finding are really just an expression of, hey, what's the coefficient I need on the first term in the y equation? Hey, what's the coefficient I need on the second term in the y prime equation where a negative 2 fell out front because of derivative? Well, I need 1 and negative 2. That's exactly what my eigenvector is. So the eigenvector is carrying that information. Now, I'm going to have plus C2, and then it's going to be some stuff, and then there's going to be a t e to the negative 2t. And then what is this stuff? Let me find a different color. I'll find pink. This stuff here in pink, check it out. What's, forgetting about the C2, the t in the e to the negative 2t, what's the coefficient on all that razzmatazz? The coefficient is 1. And then in this term for the y prime equation, what's the coefficient of C2 t e to the negative 2t? It's negative 2. Okay? So I've got C1 times eigenvector times exponential plus C2 times eigenvector times t times exponential. That feels totally normal based on where we've come from, but because I'm tracking these two things at the same time and because the second row is the derivative, I've got this little extra bit of stuff right here, and this little extra bit of stuff would produce a third term, and that third term has to do with the generalized eigenvector. So this thing, this last bit right here, this is why we get another vector. What do I call this vector? I call this vector the p vector. And then the question will come up, how do we find this p vector? Well, here's the resolution to the problem. And for those that want to see a more detailed derivation, instead of this rule of thumb, we must assume in the repeated root case that the second solution is t v e to the lambda t, which is totally like what we felt for the repeated root case, but you pick up this little extra bit of stuff, which is p e to the lambda t. We call this a generalized eigenvector, and if you shove this assumption back into the differential equation, you will find that this generalized eigenvector p obeys the equation a minus lambda I times the p vector is equal to the v vector. Okay. So that's the background. That's the quicker way to explain the background. But what we want to do in the next slide is to just use it, right? We have a game plan for complex roots. We have already this eigenvalue, eigenvector stuff for repeated roots. Now we've just noticed that if we looked at y and y prime from a second order equation, we get this extra vector because of the product rule coming about because of this t multiplication. And when I do the problem with vectors instead of just scalars, I have to keep track of that little extra bit, and that's called the generalized eigenvector. Questions? Okay. Oh yeah, what's up? That last little bit seems a little bit arbitrary. It is super duper arbitrary, and I can show that in example. So I'm going to fade. I'm going to freeze. I'm going to move over to the next slide, which is basically this slide where I've gotten rid of the purple and the red stuff, except for the red equation, the equation that I have to use. The statement in chat is like, man, that kind of seems like it's floating around and being arbitrary. It totally is. It exists only to satisfy initial conditions, and it has a lot of variability, as we're about to see. So I'm going to switch over in 3, 2, and 1. Okay. We have x1 vector is equal to eigenvector e to the eigenvalue t. We have that. We figured that out from the last round. This is just us writing it down. Now, x2 vector is going to be t times 1 negative 2 times e to the negative 2t plus p vector times e to the negative 2t. And then the question is, what is this? The answer to this question is, it must obey this equation. So, let's just do it. I have a minus lambda I times the p vector. So I take my A matrix, I subtract my eigenvalue off the main diagonal, so I have 0 minus a minus 2, so I have a 2, I have a 1, I have a negative 4, and then a negative 4 minus a negative 2 would give me a 2. Notice that these two rows are multiples of each other. That's them again saying they're giving me the same directional information, multiplied by a P1 and a P2. So this is very familiar to everything I've been setting up till now. And now what goes on the right-hand side isn't the 0 vector. If it was the 0 vector, this would be the eigenvector equation. But what I have here is a generalized eigenvector, P, and to get that generalized eigenvector, I set this A minus lambda I times P equal to the V vector. And as before, There's not a 0 on the right-hand side, but I play the same game. So I get a 2 times a P1 plus a 1 times a P2, and that is equal to the number 1. I will highlight that in yellow. That is first row onto first column. Gives me the number 1. And so now I'll figure out what my P vector should be. I'm going to say let P1 equal 0. If P1 is equal to 0, then P2 is equal to 1. And then my P vector will be equal to 0 and 1. And so then what is my second solution? My second solution is T1 negative 2 times e to the negative 2t plus the vector 0, 1, e to the negative 2t. So that's the piece of the puzzle we need for the repeated root problem. We need this generalized eigenvector equation. We need to know how it fits into the second solution. And then we just got to do our normal thing. Questions? Whew, that was tough to do. I wanted to give you a minute to think. And yeah, not talking for a straight up minute. That's uncomfortable for me. I'm used to just standing here and talking or being in front of a board and talking. Let me tell you about the questions that I would normally get at this point. This step right here where the cursor's at, that probably made some of you uncomfortable. It probably made some of you uncomfortable because you should be getting used to never choosing V1 or V2, the components of your eigenvector, to be 0. And so the reason why you don't choose them to be 0 is you have to avoid the 0 vector. But notice here, I set my P1 equal to 0, and then my P2, because of this non-zero right-hand side, it turned out to be not 0, so my P vector is not 0. And I did this so that it would match the previous work that we had done on the second order problem. Now, if that makes you uncomfortable, right? I was doing it for correspondence, but if it makes you uncomfortable, you could have just said, let P1 equal 1, which is totally normal. And then if P1 is equal to 1, I have 2 times 1 plus P2 is equal to 1, so that P2 becomes negative 1, and then my generalized eigenvector P could have been as well the vector 1, negative 1. And then I think that gets into Caleb's question, seems super arbitrary, and it is, because remember, you're going to multiply both x1 and x2 by constants, and it turns out that the generalized eigenvector can be arbitrary as long as it obeys the equation for the generalized eigenvector. It's just that the constants adapt to whatever you put into this generalized eigenvector so long as it obeys this equation. All right. Well, those are the last of our rules. We have now hit 250. And so maybe for the first time in forever, I will end class appropriately on time. And I am now going to take a second and make sure that I press the stop record button so that I just don't run out of lecture. So have a good weekend. Let me know if you have questions. Recordings are stopping now.
Recording stopped.